We will see another technique used in out of order processor known as register renaming. So last class we have seen what do you mean by out of order processor. Out of order processor, what do you mean by out of order processor? The instruction will be written in a particular order, but out of order processor can pick up any instructions from any part of the program as far as dependencies are met. So out of order processor can execute the instructions in a different order from that you have written the program. So here in the out of order processor, a register renaming is used to eliminate the write after read and write after write hazards. Last class we have seen what do you mean by write after read and write after write. What do you mean by write after read? One register should be written only after the read of the same register has been done by some other instruction. Right. So first of all, one register should be read by one instruction, then only it has to be written. That is known as write after read hazard. That is a normal execution. If it is not happening in this manner, that means first write is taking place, then if read is trying to take place, then it is known as write after read hazard. Similarly, write after write. So let us take you are having two instructions. First instruction should write the result, then only second result is supposed to write the result to a single register. But if this order is not taking place in the same manner, that means if the second instruction is writing first, followed by the write of the first instruction, then write after write hazard will take place. So register renaming is a technique used for eliminating both these hazards. So how it will eliminate both these hazards? It will add some non-architectural renaming registers to the processor. So certain additional non-architectural elements such as renaming registers or temporary registers will be added to the processor in order to eliminate these hazards. So for example, a processor has added say 20 renaming registers. For example, T0 to T19. Right? Let us take 20 renaming registers has been added in a processor. So the programmer will not be able to use these registers directly. So as a programmer, I cannot use these registers in the instruction directly. Why? Because it is not part of the architecture. So T0 to T19, it is not part of the actual architecture. In my architecture, I will be having say 16 registers, several ALUs, program counter, etc. But since these temporary registers are not part of the architecture, that is why it is known as non-architectural elements. So programmer cannot use it directly. But the processor can use it in order to eliminate the hazard. Whenever processor finds that if you are replacing an existing register with a renaming register or this temporary register, it will eliminate the hazard. Then processor can use them. But programmer cannot use it directly. We'll see one example here. So let us take this is a last program what you have seen. This is out of order processor program what you have seen in the last class. So first of all you are using LDR, then you are using OR, STR, add, sub and AND. So here you can see that between add and sub there is a write after read hazard. That means the sub should write into R8 only after read from the R8 in add instruction is over. If it is done in the reverse manner, that means if sub is written first, then only reading of add is taking place, it will generate write after read hazard. So why this hazard has occurred? Because both these instructions are sharing a same variable known as R8, right? And this R8 will be available only after loading of the memory content to R8 using the LDR instruction. So once the LDR instruction is executed, we need to wait for 2 cycles because LDR is having load instruction is having a 2 cycle latency. So add can be executed only in the third cycle. This is first cycle, second cycle, third cycle. So that is why add is executed here, because after executing LDR, 2 cycles you need to wait, or latency of 2 cycles is there. So in the third cycle only rate can be read by the add. Right? So why this problem arose? Because in both the instructions we are using rate. And specifically why this right after read hazard came, we are sharing the same register in add and sub. So if we are replacing these two register, or specifically if we are replacing this register, let us try to replace this register. If you are replacing the register write of sub instruction with the renaming register, set T0, what will happen? This instruction will become an independent instruction. So if you are replacing this write with the T0, what is happening? This sub instruction need not wait for this read from write in add, because we are not sharing the same write. Another register T0 is used. So if you are using T0 instead of sub, we need not wait for read in add instruction, and we need not wait for the load instructions latency. So we need not wait for read of write in add, and we need not wait for load instruction 2 cycle latency. So what will happen? Sub can be executed more sooner. So here sub was instruction executed as a fifth instruction. Since I have replaced R8 with T0, you can see here. Here I have replaced R8 with T0. So instead of executing it as a fifth instruction, here we were able to execute it as a second instruction itself. Why? Because T0, R2 and R3, all the three are independent registers. So once the load instruction is executed parallelly in the same cycle itself, because it is a two-way out of order processor, so two instructions can be fetched. So in the first case, why OR was fetched here? Actual order of the program was different. Actual order was LDR, then it was these instructions, add, sub, etc. But why OR was executed here? Because the add and sub, if we need to execute this, we need to have a 2 cycle latency because of usage of R8. But here what you have done, I have replaced this R8 with T0. So instead of executing sub in the third cycle, we were able to execute it in the first cycle itself along with LDR. So instead of OR, we are executing the sub instruction, because it is all the three are independent instruction. So sub instruction need not wait for 2 latency and need not wait for read from R8. So right after read hazard we have overcome. And one more thing you need to keep in mind, whenever you are changing a particular register with a renaming register, the processor should also rename the subsequent register. So here you can see sub R8, R2, R3. In the next instruction, that is in AND, R8 is again used. So if the processor is renaming this R8 as T0, the subsequent instruction where this R8 was used previously, that instruction also should be renamed. Since add was executed here, the sub was executed here, and can be taken to the second cycle. Previously, you can see that in the second cycle, only one instruction were there. So the remaining logic was left unused. Right, you can see here, when you are using store, the remaining portion of the logic was was unused, because instead of accessing 2 instruction in one cycle, only one instruction was fetched. Why only one instruction was fetched? Due to the dependency of R8. R8 will be only available after 2 cycle latency. So in the second cycle, only store was able to execute, because the next 3 instructions were dependent upon R8.
add, sub and all the three instructions were dependent upon R8. It will be available only in cycle 3. So in cycle 1, in cycle 2, only store could be executed. So the remaining logic was kept unused. So it is a wastage of resources. But using the renaming technology, register renaming technique, what you have done, the AND has, which was executed in the third cycle, fourth cycle, it was taken to second cycle because the previous sub instruction was executed in the first cycle itself. So AND can be taken to the second cycle, and we need to keep in mind the processor should rename the subsequent register also, which is present in AND. Right, because in the AND also R8 was there. So though that R8 also should be renamed with the T0. So both sub and both the registers R8 register should be replaced with the T0. Then in the second cycle itself, the OR instruction also can be executed. So and OR can be executed in the second cycle, and the third cycle add and store can be executed. Right. So by adding a renaming register methodology, what you have done, you have increased the throughput. How you have increased the throughput? Instead of executing one instruction in the second cycle, we were able to execute two instructions. So wastage of resources was not there. And in the previous case, the whole 6 instruction lines were executed in 4 cycles. First cycle, second cycle, third cycle, fourth cycle. But by using register renaming technology, here we were able to execute 6 instructions in 3 cycles. 6 instructions in 3 cycles. But even though certain read after write hazard is there, that will not create much problem. We were able to increase the instructions per cycle by 2. Previously we were having 6 instructions by 4 cycle, well, that is 1.5, but here we were able to execute 6 instructions in 3 cycles. So we are able to increase the instruction per cycle to 2. So right after read hazard, the sub and instructions were based, the right after read hazard has taken place because sub and instructions were reusing R8. So here what you have done, we have renamed R8 to R0 for the sub instruction. So sub instruction was executed sooner, that is before add. Before add itself it was able to execute. But in the previous case, only after add it will be executed because otherwise right after read hazard will be there. But in this case, sub was executed even before add instruction because there is no dependency here now, because sub it is using a T0, add it is using R8. So sub can be executed even before add because there is no dependency. And the processor will keep a table of registers which are renamed. So it can rename the registers in the subsequent dependent instruction also. That is what here I told. Whenever sub is renaming R8 to T0, subsequent instruction register also should be renamed. For that, the processor will keep a table of registers which are renamed so that it can be easily renamed. So this is an example showing the register renaming technique. Then we will see one by one. In the first cycle, what is happening? LDR will be issued. We have seen already. Then the add instruction is dependent on LDR by R8. Add instruction is dependent upon LDR by R8. So it cannot be issued. Instead of that, sub instruction is issued because it is independent now. So instead of issuing add is not cannot be issued here because it is dependent upon R8. Instead of that, sub will be issued because R8 was replaced by T0. So in first cycle, LDR and sub was issued. In the second cycle, what is happening? Again, since there is a 2 cycle latency for LDR, sub and cannot be executed, and add also cannot be executed. So in the case of cycle 2, LDR instruction and a dependent instruction Say, so add cannot be issued here. Why add cannot be issued here? Because R8 is dependent upon LDR. So instead of that, what will be issued? Both and or can be issued. And or, that is these two instructions. And or, these two instruction can be issued here. Because and is again dependent upon T0. T0 was available in the previous cycle, or is not at all dependent upon any of the previous registers. So or also can be executed. So and or will be executed in second cycle. In third cycle, what is happening? Since R8 is available now, R8 which is part of LDR is available now, add instruction and str instruction can be executed. Why add can be executed? Because R8 is available after 2 cycle latency of LDR. And why str can be executed? R11 is also available, which is generated as a result of OR. So in third cycle, add and str will be executed. So by incorporating the register renaming mechanism in out of order processor, what was the result? We were able to issue 6 instructions, that is 2 instructions per cycle, right? So 6 instructions were able to be executed or issued in 3 cycles. This is first cycle, second cycle, third cycle. So in 3 cycles, 6 instructions we are able to issue. So what is the instruction per cycle count now? 6 by 3, that is equal to 2. Previously it was 1.2 and 1.5 in two different methodologies. Now we have increased the instruction per cycle execution to 2 by using register renaming technique.